Good morning, everyone. Before I start my talk, I'd like to just take this opportunity to thank the organizers of this wonderful conference for their kind invitation. The title of my talk is Computational Challenges in Multiscale Poromechanics, and I'm going to address two types of multiscale phenomena, the first one being the persistent shear bands in granular materials, and the second one is the multiscale porosity in terms of two dominant porosity scales, also called double porosity material. Now, persistent shear band is normally encountered when we have heterogeneous materials. For example, a material may have a spatially varying distribution of density as well as degree of saturation. And in that case, the commonly used notion of bifurcation analysis may not necessarily directly work, as a result of the fact that we might have to wait for the actual persistent shear band, which is the dominant pattern of localized deformation, to emerge, as opposed to just introducing enhancements to the solution. So for example, this slide here shows snapshots of the so-called determinant function or localization function, which is commonly used to determine the onset of bifurcation. Red implies close to bifurcation, and other colors are above bifurcation, which means stable. So we see here at 3.84 millimeters, there is a localized deformation emerging on the left vertical face. And then if we compress the sample further, we see that there's actually no localized deformation forming, but it's more diffuse. Now, at 4.36 millimeters, we see that another shear band is emerging on the right vertical face. The question, therefore, that we want to answer is this going to be the persistent shear band? Or will we have a conjugate band forming as a dominant pattern of localized deformation? Now, as far as multiscale porosity, there are several applications, most specifically in geomechanics, where a material may exhibit two dominant porosity scales. Examples include fractured rock, where you have the porosity of fractures as compared to the porosity of matrix being so distinct with respect to each other. And then in the other context, we have so-called aggregated soils, where we have macropores that are many times more permeable as compared to the micropores. So in the context of double porosity, I'm simply going to use the terminology micropores and macropores, although the notion can also be applied to fractured materials. So here's the outline of the presentation. First of all, I'm going to talk about coupled solid deformation and fluid flow in the spirit of this conference. Then I'm going to discuss heterogeneity in density as well as in degree of saturation. The underlying reason being that these two parameters or quantities can actually be quantified non-invasively and non-intrusively in the laboratory. Then I'll talk about double porosity, and finally stabilized mixed finite elements. Now, in terms of heterogeneity, as I mentioned earlier, there are several non-invasive, non-intrusive, non-destructive way of quantifying the spatial distribution of density as well as degree of saturation. And most of these are based on CT imaging. The left image shows CT image of a spatially varying distribution of density of sand. You can see there that the light region over in this portion is a pebble or a piece of rock. Now, degree of saturation can also be quantified spatially in a non-invasive way. For example, this is the degree of saturation. Red implies close to 100% saturation, and then blue is close to 0% saturation or almost perfectly dry. All of this motivate the spirit of quantifying heterogeneity for purposes of bifurcation analysis eventually. Okay, so let me just recall the basic equations for single porosity formulation, and then I'm going to talk about double porosity formulation subsequently. Now, we use theory of mixtures, where volumes can actually be subdivided into a number of phases. In the following discussion, I'm going to consider solid water and air mixture, and we have the following definition of volume fractions: phi sub s, W, and air nothing else but the superscripts denoting solid, water, and air. And the volume fractions are required to satisfy the closure condition, the sum being equal to 1. Next, we also introduce degree of saturation, or recall the degree of saturation, which is the ratio between the volume of water to the volume of the voids. So 1 minus V sub S right here is nothing else but the volume of the voids. Now, the mass density can also be added or partitioned using partial quantities. Rho sub S, W, and A are the partial mass densities of solid, water, and air, respectively. And then finally, we have a pullback total mass density, which is nothing else but the current mass density pulled back by the Jacobian of the deformation of the solid phase. And here we recognize that the pullback mass density is actually not a constant, but it is variable, the reason being that there's relative flow taking place between the solid, water, and air. Now, we need to satisfy a number of conservation laws, including the conservation of solid mass, and this slide here focuses on that conservation. J, rho S, and Vs represents nothing else but the total mass of the solid contained in a unit volume. And then if we take the material time derivative following the solid phase motion, then of course, if there's no mass exchange between the solid and the fluid, the right-hand side must be equal to 0. If we consider solid to be incompressible, then rho sub S can be factored out of that material time derivative operation, and we have a much simpler expression. Now, the result can be expressed in a number of alternative forms, which is nothing else but the integration of this material time derivative, where V here is the specific volume, that's the initial value, J is the Jacobian of the solid phase motion. Also, we need to impose the conservation of water mass. So in the first equation, we have the Eulerian relative flow vector expressed in terms of the volume fraction for the water, the intrinsic mass density for water, and the relative velocity of water with respect to the solid. Now we introduce the Piola transform because we are ready to implement this in the context of finite deformation. So this is the Piola transform of that Eulerian relative flow vector. F here is the deformation gradient for the solid motion. And also the Piola identity, which is well known in nonlinear continuum mechanics. And finally, we have the law of conservation of mass for the water phase, given by this very simple expression. And I think this is the simplest possible expression. You can write the law of conservation mass for the water. Rho sub 0 here is the pullback mass density of the solid, and then you have the material time derivative there, the Lagrangian divergence, and the Piola transform. Next, we also impose the conservation of linear momentum. And here we're going to make a simple assumption just for the sake of argument, although this is not a limiting assumption for the formulation. First, we assume that we have a passive air, and that is the air pressure in this mixture of solid water and air is equal to 0. And then we also assume that the BO coefficient B is equal to 1, which is a realistic assumption mostly for soils. Now here we have an expression for the effective Cauchy stress tensor. Considering those assumptions, sigma is the total Cauchy stress tensor, sigma bar is the effective stress tensor, and then we have SR here, the degree of saturation, and the water pressure. So this is quite similar to the Terzaghi effective stress, except for the fact that we have the degree of saturation appearing. And then we accommodate for finite deformation effects. This is the first Piola. Tau is the Kirchhoff stress. And then we write the balance of linear momentum, the right-hand side being equal to 0, assuming that we have a quasi-static condition. Now we go to the first law of thermodynamics, and this actually will assist us in identifying expressions for the conjugate variables. For example, the first variable or the first quantity appearing on the right-hand side of the expression for the rate of change of internal energy shows us conjugate relation between the effective Cauchy stress tensor or Kirchhoff stress tensor and the rate of deformation for the solid. And that leads to the definition of the effective stress. Now I'm going to go to the third term on the right-hand side, which relates the suction stress, the relative velocity of water with respect to the solid, and the volume fraction for water. This leads to the fluid flow constitutive law commonly used in the form or represented by Darcy's law. And then the second term on the right-hand side of the expression for the rate of change of internal energy. We have here three terms, not two. S is the suction stress, 1 minus Vs is the porosity, and SR, we recall, is the degree of saturation. So this leads to the water retention constitutive law consisting of three terms, not two. This tells us or suggests that we must have a relationship among three variables, including the degree of saturation, porosity, and suction stress. Or that the degree of saturation should be expressed as a function of the specific volume or the Kirchhoff suction stress. Or that the degree of saturation should be expressed in terms of the Jacobian of the solid phase motion and the Kirchhoff suction stress. Now, an example of this type of constitutive law is represented by the law proposed by Gallipoli et al. Way back in 2003, which is of this form. And as we can see here, the degree of saturation, specific volume, and suction stress appears in that constitutive equation. Now, this particular constitutive equation reduces to the simplified Van Conooten relation for a deformable solid matrix. Here's a representation in three-dimensional picture of the water retention law. It is a surface and it's not a curve. It relates us the degree of saturation, the specific volume, and the Kirchhoff suction stress. Now, of course, we have one surface of this type for wetting, and we expect that there has to be another surface for drying. Next, I'm going to show that everything can be encapsulated in UP form, where U is the displacement of the solid and P is the pore water pressure. First of all, we consider the balance of linear momentum for the mixture. So the first term here involves the effective Kirchhoff stress, tau bar, which, as we know, can be expressed in terms of the displacement of the solid matrix and the suction stress. Now, as part of the variational equation, we also have the degree of saturation. And we determine the degree of saturation to be a function of the Jacobian determinant of the solid phase motion as well as the Kirchhoff suction stress. And then the pullback mass density appearing on the left-hand side, notice here that I didn't throw it into the right-hand side because rho sub O is not constant. And once again, we determine it to be a function of the solid phase deformation as well as the degree of saturation, which is in turn a function of the solid phase motion and the Kirchhoff suction stress. So obviously we have a UP formulation. In other words, the independent variables alone can be determined to be the displacement of the solid matrix as well as the pore water pressure. Next, we consider the balance of water mass, recalling once again that we assumed in the first place that the air pressure is equal to 0. So we only need to consider the balance of mass for the water phase. And this is the variational equation in time-integrated form. First of all, rho sub 0 here has already been determined to be a function of the solid phase motion and the pore water pressure. Next, we have the Darcy velocity, which is given by this particular expression here, a function of the relative velocity of the water with respect to the solid. There's that Darcy velocity, there's permeability or hydraulic conductivity. We shall show that hydraulic conductivity can also be expressed for deformable porous material in terms of the solid phase motion as well as the pore water pressure. Now, the constitutive model is something for the solid matrix is something that is quite tricky to implement, considering that we anticipate very complicated constitutive laws or properties for the solid. So in this particular simulation, at least, we implemented a variation or a variant of the critical state soil mechanics, where we implemented a three-invariant model. And we have here a number of yield surfaces that vary with respect to the suction stress. So this is a single porosity or single porosity formulation with a single yield surface, except for the fact that the yield surface varies with the suction stress. Now I'm going to go to constitutive modeling and show that the hydraulic conductivity as well can be expressed in terms of the solid phase motion and the pore water pressure. So here the hydraulic conductivity is linearized in terms of J as well as the degree of saturation. This is backed up by a number of experimental observations and constitutive laws. For example, the Goseni-Karman constitutive law for the hydraulic conductivity tells us that the hydraulic conductivity varies with the porosity of the material. The Brooks-Corey relation, very commonly used in hydraulics, tells us that the hydraulic conductivity is also a function of the degree of saturation. So clearly, we have a UP formulation. Now I'm going to go ahead and just illustrate one particular example of localization analysis in the context of heterogeneous material with single porosity, and then later on, I'm going to go to double porosity formulation. So in this particular simulation, we generated a randomly distributed specific volume. So all we did here was consider a MATLAB program, specify the mean value that we want, the standard deviation, and the range, the maximum and minimum values. And then this is one realization for the specific volume. Now, we prescribe a uniformly distributed suction. We have no way experimentally in terms of determining the spatial distribution of the suction stress, so we assume it to be uniformly distributed. Now, consequently, we obtain the spatial distribution of degree of saturation. Note here that we did not generate the degree of saturation spatial distribution stochastically or statistically. It was determined from the fact that we have a relationship among degree of saturation, specific volume, and suction stress. So we need to specify two, and then we can determine the third. And then all we did here was to consider a plane strain compression. The out of plane is the direction where there is no deformation. So we specify pressure on the two vertical faces and then apply a vertical compression. Here's the distribution of the suction stress, showing at a certain point in compression the emergence of a persistent shear band in this particular case. And this is backed up by the spatial distribution of the degree of saturation. We note here that along the shear band, we actually have an increasing degree of saturation. The reason being that the sand is initially loose, and when this shear band is compressed, we have a compactive shear band. We essentially have the pores, the air pores, being squeezed out, resulting in the degree of saturation increasing, and therefore the fluid is being expelled from the shear band into the body of the material. Here's a plot of load as a function of the vertical compression. Note here that I am not plotting stress versus strain. The reason being that I am considering the problem as a boundary value problem. It is not an element problem. We're considering the spatial heterogeneity in the different parameters. So if we have conducted here two simulations, one where we have a perfectly homogeneous material and one where we have a heterogeneous material. I forgot to mention that the heterogeneity was very, very slight. The specific volume was almost uniform. The only perturbation here is very minimum, and yet when we plot load as a function of vertical compression, one curve plots on top of the other initially, and then there is a bifurcation in the slightly heterogeneous simulation, whereas no bifurcation has been detected for the perfectly homogeneous simulation. Now, we also investigated the effect of strain rate. The faster the strain rate or the rate of loading, the earlier we detected bifurcation. And the reason for this was because of the fact that the presence of the fluids as well as the accompanying fluid flow actually imposes a volume constraint, and therefore it alters the point of localization for the material. We can also note the bifurcation occurring on the soil water retention surface. There are 2 points. Point A is a point situated away from the shear band. and point B is a point located within the shear band. And we see that point B is bifurcating with respect to point A when plotted on the soil water retention surface. Next, I'm going to go to double porosity formulation. Now, in double porosity formulation, we recognize that there are two distinct definitions. One is based on the definition of dual porosity, where it is assumed that fluid simply migrates within the macropores, but stays stagnant within the micropores. Now, there is also another notion of dual permeability, where fluid can migrate not only within the macropores, but also within the micropores. And that is the formulation that we have adopted into this particular formulation. So this is the double porosity representation in terms of the phase diagram. Conventional phase diagram on the left-hand side shows us a mixture of solid water and air. And then all we did on the right-hand side is we subdivide into macropores and micropores phase diagrams. For the micropores, we see here that we have a physically unsaturated phase diagram where part of the volume is an empty space. That empty space is represented by the macropores. And then superimposed with that is another physically unsaturated phase diagram where you have more empty space here, but that full space right there represents the macropores, which is composed of liquid and gas. Okay, so let me go back again to the thermodynamics of the problem. This one here is the definition of the effective stress for three-phase material, solid, water, and air, with two dominant porosity scales. So the expression is very similar to the one that I showed earlier, except for the fact that the mean pore water pressure here is equal to the average mean pore pressure in the micropores and the macropores, weighted according to the void fraction. And this is the expression for the momentum balance equation. Note here, even though we're considering a quasi-static condition, the right-hand side is not equal to 0, because we are accommodating for the exchange of fluid mass between the micropores and the macropores. Once again, the double porosity formulation needs to employ the concept of internal energy in order to recognize conjugate variables. So this is the expression for the rate of change of internal energy for a solid water-air mixture with two dominant porosity scales. The first term appearing on the right-hand side shows the conjugacy between the effective stress and the rate of deformation for the solid. This leads us to the definition of effective stress. Now we have Darcy's law now taking place at each of the two pore scales, and that is represented by the second term on the right-hand side. The third term here represents the water retention law at each pore scale. We have, in fact, magnified the problem 2 times as a result of this. And then the mass transfer term also appears on the right-hand side of the expression for the rate of change of internal energy. And finally, there is this extra term on the right-hand side that at this point, we cannot still physically explain. The reason being that we don't have any experimental evidence that shows that this relationship is indeed meaningful. So the finite element formulation is very similar to the two-phase formulation with solid and water, at least for the fully saturated material, except for the fact that we have accommodated the pore pressure variable in the micropores and the macropores. So we have an expanded mixed finite element where there are 2 pore pressure degrees of freedom at each node in addition to the solid displacement degree of freedom. So we employ the backward implicit time integration. The problem is now going to be considerably larger than it is for the single porosity case. So we also employ a Newton-Krylov solver with block preconditioning. And here's one example of the fact that we can actually accommodate the spatial variation of macroporosity. Case number 1 and case number 2 are 2 realizations of the distribution of macroporosity. And we employ the same compression, vertical compression simulation. And we obtained 2 conjugate shear bands, one going this way, the other one going that way. And this simply tells us that the spatial distribution of macroporosity does influence the ensuing shear band. Here's a display of the overall degree of saturation. If you take a look at the degree of saturation for the two cases, they are less than 100%, meaning to say our sample remains physically unsaturated, hydraulically unsaturated. And yet, if we consider the overall water pressure, then we have the water pressure greater than 0. So this kind of anomaly is something that we cannot explain with the single porosity formulation, having a positive pore water pressure and a partially saturated mixture. In the undrained limit, and this is the last topic that I'm going to talk about, we have to also consider the fact that our system could suffer from the Lbv instability associated with volume constraint, except for the fact here that we now have to accommodate for two pore pressure variables. Once again, we revisit the finite element formulation of this form. Unlike single porosity, there are two kinds of undrained condition. We can only have micropores being undrained, and if that is the case, then one submatrix in the 3x3 block matrix would be equal to 0. Or we could have both the micropores and macropores being undrained. In that case, then we have a larger block being equal to 0. Now, the stabilization term should be such that it should be large enough to circumvent Lbv instability, but small enough to not include numerical artifacts. And here we consider the performance of the proposed stabilization using the higher order intrinsically stable Q2P1, equal order unstabilized Q1P1, and a stabilized Q1P1. And then we make a comparison. So this is similar to the cryosphere problem, except for the fact that we have accommodated for the spatially distributed or varying pressure outside of the sphere. And this is just one octant of the sphere. Macropores, micropores. This represents the solution using the higher order elements, and we don't see any pore pressure oscillation. On the other hand, when we make use of the unstabilized Q1P1 mixed elements with two pore pressure variables, we see oscillation in the micropores. Actually, there's also oscillation in the macropores, but not so visible. Now, in order to circumvent the problem, you consider a so-called two-fold saddle point, which has this generic form. Actually, the detail can be obtained from the paper by Howell and Walkington. Now, Howell and Walkington showed us that for a two-fold saddle point problem, we can actually reduce it to a single saddle point problem simply by using a nested inf-sup condition. So this is the relevant inf-sup condition for the two-fold saddle point problem. This is all of A, B1, and B2 are bilinear operators. Now, we are particularly interested in the combination where these constraint bilinear operators, B1 and B2, actually belong in the same Sobolev space for the two pore pressure fields. And in that case, we have the relevant inf-sup condition for the two-fold saddle point problem treated as a nested single inf-sup condition as follows. And once mathematics plays out, it actually tells us that the relevant inf-sup condition can actually be expressed in terms of the inf-sup condition for the single saddle point problem by simply using the mean pore water pressure. So in that case, we can have the weaker inf-sup condition given by Borja, which has already been well known in the field of computational mechanics in terms of the polynomial pressure projection stabilization, now being applied to the mean pore water pressure. And this is the last example. We recall the sphere problem. Higher order elements, no pore pressure oscillation. We recall that if we use the unstabilized Q1P1 element, that there is pore pressure oscillation not only in the micropores, but also in the macropores. And then we use the stabilized Q1P1 element, and we were able to get rid of the spatial oscillation of the pore pressures. This is a strip footing example that shows the same efficacy of the pore pressure polynomial projection. This is the unstabilized element, Q1P1, and with stabilized, we remove the pore pressure oscillation. So let me just conclude with the following. There are three types of heterogeneity considered in this work: density, degree of saturation, and macroporosity. The double porosity formulation is new. It's based on a thermodynamically consistent effective stress. The stabilized finite element formulation is also new and circumvents the instability associated with volume constraints. These are the acknowledgements, and I thank you very much for your attention.